So we have another 2.2 exercise that we're going to do together. That's very important. And then we're going to have a bit of a theoretical discussion for the rest of this section. So let's do the exercise. We're going to do another one of these inverse calculations where we want, in this case, we want to show that this matrix is not invertible. Now, you really don't need to know this ahead of time. You just start the process, and it either works or it doesn't work. And so we want to see, what does it mean for it not to work? This is another 3 by 3, like our previous example. So I'm going to write these columns next to 1, 0, 0, 0, 1, 0, 0, 0, 1. And again, if you like to put the dotted line in, you can, and some people put that all the way through the process. And now we're going to apply our row operations. And I'm going to take row 2 and replace it with row 2 minus 2 times row 1. Row 3 I'm going to replace with row 3 plus row 1. 1, 6, 4, 1, 0, 0 stays the same. I get 0. Let's see, I think negative 8. I'm going to take negative 1 plus negative 8 is negative 9, I believe. And then I'm going to have minus 2, 1 minus 0, 0 minus 0. For row 3, I get 0, 8, 9, 1, 0, 1 at this point. And now what I notice here is, before I try to get a 1 in another pivot position, notice these opposite values. I have the negative 8, 8, negative 9, 9. So I'm going to replace row 3 with row 3 plus row 2 at this point. Not worry about the pivot right away. 1, 6, 4, 1, 0, 0. 0, negative 8, negative 9, negative 2, 1, 0. And what I'm going to get here, if I add row 2 to row 3, I get 0, 0, 0. I'm going to get negative 1, 1, 1. And here's where I have to recognize that there's some trouble, because there's no way, to get a pivot position down here, to get a pivot in row 3, or to get a 1 in row 3, or to get 0, 0, 1 at this point. So that's where I know that my A matrix is not going to reduce to the 3 by 3 identity matrix. So it's just the row of zeros, by the way. Row of zeros is the trouble, so don't worry about the reason. As soon as you find that row of zeros, again, for just the A part of this matrix, then we know that A is not invertible. All right, so we're done with that exercise. Whoop, there we go. All right, let's talk about the rest of our handout then, a little bit of this theoretical discussion. And the point of some of this we'll use later on, and also we'll have a justification for this process that we use to find an inverse. Like, why does that work? What's going on there? So we need some more vocabulary, and first we talk about an elementary matrix. An elementary matrix is any matrix obtained from the identity matrix by performing one row operation. So here's just some examples. Here's the identity matrix, the 3 by 3 identity matrix, and I picked 3 different row operations to do. I'm going to replace row 2 with row 2 minus 3 times row 1. So I'm going to apply it to the identity. This is what I obtain. I'm going to take row 2 and just multiply by 4, and this is what I obtain. And then I'm going to interchange 2 rows, row 2 and 3, and this is what I obtain. And I guess, I don't know, I number them this way. I call this one E1, E2, E3. So these illustrate one of each of the 3 kinds of elementary row operations, right? So performing an elementary row operation on a matrix can always be represented as multiplication by a particular elementary matrix. This is a brand new idea, and it's like, what? So let's look at some examples of this. And so what I'm going to do is I'm going to take each one of these, I think E1, E2, and E3, and I'm going to, I picked out this matrix A, so this is just one I made up, 1, 0, 3, 2, negative 1, 5, 0, 8, negative 2. And I'm going to multiply A by E1 on the left, okay? And so here's my E1 from the previous page. Here's my A from this example. And you can check the multiplication. This is what we get. And my point is, this is the same thing we would obtain if we applied that elementary row operation to the matrix A. So remember, E1 was defined by replacing row 2 with row 2 minus 3 times row 1. So if we take A and replace row 2 with row 2 minus 3 times row 1, we should get negative 1. Yeah, we should still have a negative 1 there. We have 5 minus 9 is negative 4. All the other entries are the same. E2, what was E2? E2 was just interchanging 2 rows. If we multiply A by E2 on the left, what happens is we get 2 rows interchanged. And I guess, sorry E3, you don't get a chance to participate. All right, so all elementary matrices are invertible, and their inverse matrix represents the reversing row operation. Every row operation can be reversed, and it takes you back to where you would have been right before you performed that operation. So Theorem 7 of Chapter 2, in what our book calls Theorem 7, a square matrix A is invertible if and only if A is row equivalent to the identity matrix. Any sequence of elementary row operations that takes A to the identity matrix will also transform the identity matrix to A inverse. This theorem justifies our process for finding A inverse by working with row operations, just like we did in the 2 previous exercises. So the proof of this theorem is on the handout. I'm not going to go through these steps with you together. This in the next page, on page 6. I'll leave it for you to read on your own. This is all posted in Canvas. And that's the end of our 2.2 discussion.